Good afternoon, everyone. I'm Varivashya Poladi.
I'm Anishka Vaitla.
And I'm Sannidhi V. Hebbar. And we're very excited to present to you today a very intriguing paradox called the Cramer-Euler paradox, which is based on very simple mathematical concepts that are familiar to most of us.
I think by now everybody knows what a paradox is. Let us see what makes a paradox paradoxical in general. There can be several reasons for that. The first being self-reference, as we have seen in the beginning, in the Grelling-Nelson paradox that was presented by Naman and Indriyul. Another reason could be incorrect assumptions that we have just seen in Perry's paradox that was presented by our friends. Another reason could be misapplication of theorems, which is seen in Simpson's paradox.
Now, let us see what this paradox is. Cramer-Euler paradox is a mathematical paradox that belongs to the branch of differential geometry. It states that the number of points of intersection of two higher order curves in a plane can be greater than the number of arbitrary points that is required to define that curve uniquely.
The Cramer-Euler paradox is based on two theorems.
The paradox says that the number of points of intersection can be greater than the number of points which is required to define such a curve.
Why is that a paradox?
We'll get to it. That's the
Because at the points of intersection, if you consider those points, okay, gradually we'll get to know.
Yeah. The Cramer-Euler paradox is based on two theorems. The first, let us look into these theorems individually. The first one is the Bézout's theorem. The Bézout's theorem states that the number of points of intersection of two algebraic curves on the complex plane is equal to the product of the degrees of the curves, including the points of intersection at infinity and considering the multiplicity as well.
Next, let us look at the second theorem we need to understand this paradox. Cramer's theorem states that a curve of degree n can be uniquely determined by n into n plus 3 divided by 2 unique points in certain cases. Now, the first question that anyone has is what are the special conditions that define Cramer's paradox? What are the conditions that he imposes upon the curves that he's talking about? We'll look at it a little bit closely in the upcoming slides. The condition basically is that a curve should be non-degenerate, and we will be explaining to you what a non-degenerate or a degenerate curve is in upcoming slides. So basically from both of these theorems, Bézout's theorem and Cramer's theorem, what we can deduce is that they're stating that for all n greater than or equal to 3, n being the degree of the curves we're talking about, n squared is greater than or equal to n into n plus 3 by 2. And this implies that for two curves of degree 3 or higher, the intersection of the two curves would have enough points to uniquely define either curve individually. However, we have a counterexample. Consider these two curves. X cube minus x equals 10 times y cube minus y, and 10 times x cube minus x equals y cube minus y. This is the cubic curve, which is a curve of degree 3. Now, from Bézout's theorem, we know that it will intersect at 3 into 3, which is 9 points. Now, as you can see from the graph, it will exactly intersect at this 9 points. But as Cramer's theorem says, 9 points is sufficient to describe a cubic curve. Now, both of these two curves passes through the 9 points, and those 9 points will not be able to define any of the curves uniquely. In fact, these 9 points are satisfied by a parametric curve of the form x cube minus x equals a times y cube minus y. So, any of these curves will not be uniquely determined by those 9 intersection points. Now let's talk about why this is a paradox, like Sushil asked. Thing is, Cramer's theorem is true only under certain conditions, as the statement goes. In particular, only for non-degenerate cases. X cube minus x is equal to a y cube minus y, being a parametric curve, is a degenerate case. Therefore, we come to a contradiction. Why is this a degenerate case? Let's look more closely at what those are. The 9 intersection points, when substituted in a general cubic curve, give us a system of 9 linear equations, the matrix of the coefficients of which have a determinant of 0. This is a degenerate case. If you can see, the second to last and the third to last columns are essentially the same. Therefore, the debt is equal to 0, if anyone wants to verify. And now, what happens in a degenerate case exactly? Consider the simple case of a hyperbola. X squared minus y squared is equal to 0. This can also be written as x plus y into x minus y is equal to 0, which is essentially the equation of two intersecting straight lines. Now, 5 points on this line, or even an infinite number of points on the same line, will not be able to determine either the hyperbola uniquely. Hence, we can easily deduce that Cramer's theorem is only applicable in non-degenerate cases. Therefore, it's an illogical, incorrect assumption to apply Cramer's theorem in degenerate cases.
Now let's kind of sum up the paradox. The paradox basically tells us that for a curve of order n into n plus 3 by 2 points are sufficient and necessary to determine the curve uniquely. So for a conic section, 5 points are sufficient and necessary. For a cubic curve, 9 points are sufficient, and so on. But with Bézout's theorem, two curves of order n intersect at n squared points. So two cubic curves will intersect at 9 points, which is exactly the number of points that are sufficient and necessary to define it. Therefore, any arbitrary n into n plus 3 by 2 points cannot define a single curve of order n uniquely. So with this level of understanding, let us look at much more examples to make the point more clear. So here we have two curves which are of degree 4. So by Bézout's theorem, they must be intersecting at 16 points, as you see here. But by Cramer's theorem, 14 points are sufficient and necessary in general to define a curve of order 4. But you see that these two curves are passing through the 16 points, defining neither of them uniquely. In fact, these points are satisfied by the parametric curve as you see on the screen. So these 16 points are defining none of these curves uniquely. Note that this is also a degenerate case.
Therefore, we see that when the number of intersection points of two curves that we're looking at intersects the number of arbitrary points that we get from Bézout's theorem that is necessary to define a curve uniquely, we must end up at a degenerate case. Because if that's not the case, and we do have a degenerate case, non-degenerate case, then both the curves pass through the points defining neither of the curves uniquely, and therefore contradicting Cramer's theorem. This is the basis upon which this paradox is a paradox. The way we resolve this is simply to say that the paradox statement is only valid for non-degenerate cases. This is what Cramer's theorem was talking about. We cannot hope to apply both of these theorems to degenerate cases and illogically argue that the paradox holds. Now, in conclusion, we can say that this paradox is indeed a paradox due to misinterpretation and a misapplication of a theorem, in this case, Cramer's theorem. Points used are required to define a curve uniquely are not always arbitrary, and this paradox is basically inconsistent for most of the cases that we'll encounter.
Thank you for this opportunity.